Talk about phase diagram now. A phase diagram is a diagram that shows the stable phases of a pure substance or a mixture under various conditions and compositions. So for a one component system, if we're just dealing with one pure substance, okay, a phase diagram for that can be represented by a chart or a graph that has pressure on one axis and temperature on another axis. Okay, you might have the graph might be shown as not log of pressure or log of temperature, but basically you have a diagram that where you specify the conditions by just specifying the temperature and the pressure. Okay, so common features, a typical phase diagram is sketched like this. Common features of a phase diagram for a pure substance looks like this. Okay, it's divided into four regions actually, at least three regions. Here at low pressure, high temperature. These represent any point on this diagram in this region represents a condition where you expect to find your substance in the gaseous form. Okay. What happens if you were to raise the pressure of a gas at constant temperature? Eventually, what happens is it turns into a liquid. Okay. So the boundary between these two regions right here, this blue curve right here, the boundary here, each point on that boundary represents the point where your liquid and your gas coexist. Okay? So in other words, this blue curve right here is really nothing more than a plot of this blue curve is really a plot of vapor pressure of a liquid versus the temperature. Okay? So in the case of water, okay, uh, oops. Ah. In the case of water, if this was 1 atmosphere, what would this temperature be for water? At what pressure, at what temperature does the vapor pressure of water reach 1 atmosphere? 100 degrees Celsius. That's when water boils. Okay, so that's what you have there. Now, what would happen uh, if you were to if you have a liquid, so this point right here is in the liquid region, that represents a condition. The pressure and the temperature at that condition, at that point, represents a condition where you expect to find your substance in a liquid form. What would happen if you were to cool that liquid, maintaining the pressure? Eventually, what happens? So cooling means lowering the temperature, right? Eventually, what happens to it? Solidifies. Okay, it freezes. So this point right here on the green curve, so this green curve represents what? The boundary between the solid and the liquid region. That represents conditions where you expect to find liquid and solid. So this green curve right here is what you would call, which I've already overwritten with the red curve. This green curve right here is what you would call your solid, liquid, coexistence curve. Okay, those are conditions where your solid and liquid coexist. So this tells you how you can say this tells you how the melting point or the freezing point depends on pressure. You exert a higher pressure on your liquid here or your solid, you increase your melting point or your freezing point. Okay. Now, typically, this curve right here leans this way, okay? Leans to the right, but water is an exception in that in the case of water, this curve actually leans to the left. So in the case of water, if you raise the pressure of water, 1 atmosphere for water, okay, would have a melting point of what? What's the melting point of water? 0 degrees Celsius. Now, if you were to raise the pressure on the water, on the ice, you would actually be able to get it to melt, lower the melting point, okay, slightly. This is a very steep curve, so this is a very slight change in the melting point if you increase the pressure on the ice. So that's one explanation why if you were to skate over ice, okay, you're putting all your weight on that little tiny blade, okay, so you're putting a lot of pressure on the ice. That gets the ice to melt under you. That's what allows you to skate over ice. Okay. But dry ice would have the solid liquid coexistence curve for dry ice would look something like this. So if you were to skate over dry ice, the increased pressure would just increase the melting point of the ice. So the dry ice is not going to melt under you. Okay. Now down here, what do you have here? Based on the information I've given so far, this red curve right here is what you would call your solid vapor coexistence curve. Okay, that's a sublimation temperature versus pressure, or you can say that's the vapor pressure of the solid versus temperature. Okay, so that point, that curve right there. So if I have, let's just say in the case of carbon dioxide, actually 1 atmosphere is down here. So if we have solid carbon dioxide, okay, if I were to warm it up, okay, increase its temperature without changing the pressure, it will automatically directly turn from a solid into a gas without melting. So that's what happens to dry ice. In the case of water, 1 atmosphere would be somewhere up here. So in the case of water, if I were to heat up my water at 1 atmosphere pressure, it will first turn into a liquid. If I keep heating it, eventually it turns into a gas. Okay? Now, this point right here, down here, labeled TP, that's called your triple point. It's characteristic of a substance. It's very well defined for a given substance. It's a unique identifying identifying property for a substance. So water has a well-defined triple point of, it's 0.006 atmospheres. Okay, so this is the triple point of water. This temperature, the temperature at the triple point of water is 0.01 degrees Celsius. So that's 0.01 degrees above its normal melting point. Okay, so in the case of water, okay, the normal melting point, like I said, in the case of water, this curve is actually leaning this way. At 1 atmosphere, okay, at 1 atmosphere, the melting point is 0 degrees Celsius. And at 0.006 atmosphere, so this is 1 atmosphere, and 0.006 atmosphere, that's your triple point right there. That temperature right there is 0.01 degrees Celsius. So that's characteristic of water. And triple point means that's a condition where you expect to find solid, liquid, and gas all at the same time at equilibrium. Okay. Now, CP here, what does CP stand for? What do you think it stands for? Critical point, right? CP stands for critical point. That's beyond that temperature, you can no longer liquefy your gas. And so beyond this region right here, SCF, is a region where you would have what's called a supercritical fluid. Critical fluid. All right? So that's a diagram that summarizes conditions where you would find stable phases of water. Okay, you'll notice, okay, this is really a very simplified diagram, the one I've shown you earlier on the website. This is a more realistic depiction of the phase diagram. Okay.